Okay, go. Oh my gosh, you're gonna hit
Forces
me.
are a part of our everyday life. These sledders would not be able to accelerate down the hill if it were not for the force they encountered on top of the hill. A force is a push or a pull. Usually there are at least two forces acting on an object at any given time. A force can change the acceleration of an object. This acceleration can be a change in the speed or the direction of the object. In the game of lacrosse, the players will use forces to accelerate the ball. They can use it to spin the ball, change the direction of the ball, or the speed of the ball. All forces act on objects. For any push to occur, something has to receive that push. You can't push nothing. The same is true for any pull. Even if I'm swiping my hand in the air, I'm still pushing on the air, and the air is actually going to be pushing back on my hand. In these two examples, your fingers are exerting forces on the books and on the computer keys.
Just because a force is applied to an object doesn't mean the object has to move. For example, you're probably sitting on a chair right now. I'm applying the force to the chair in this direction, but the chair is not moving. And the reason why is because the floor is applying a force up on the chair as well. My force and the floor's force are equaling out, causing the chair not to move.
Forces are often represented with vector arrows. Vector arrows tell you the magnitude and the direction of the force. For example, in this situation we have two little boys pushing on one side of the chair. If we were to add together their force, let's say they both pushed with 5 newtons, we'd have a total of 10 newtons pushing on the left side of this chair, making the chair potentially go towards the right-hand side. The arrow will tell us what direction that force is being applied. So in this case, we see that both boys are pushing towards the right-hand side. The 10 newtons tells us the magnitude of the force, or how large that force is. Newtons is going to be the units that you use for force. And you've heard this unit before when we've talked about weight. In the second scenario, we have both boys pushing on opposite sides of the chair. Two things can happen here. The first situation you could have is if both boys are pushing with the exact same magnitude, 5 newtons on one side and 5 newtons on the other side. You would have equal forces canceling each other out. This is called balanced forces. And if they cancel each other out, you're going to get what's called a net force of 0. 5 minus 5 is 0. Your net force will be 0 newtons, and therefore the object will not move. This is called balanced forces. Both boys are pushing on the same object. In this case, both boys are pushing on the chair. Take note of that, because when we talk about Newton's law number 3, you're going to hear about this balanced and unbalanced forces again, and I want you to make a note that both boys are pushing on the same object, causing the net force to be 0, and the object will not move. There could be a different situation that could happen. The smaller boy could push with 5 newtons towards the right, while the larger boy could push with 8 newtons towards the left. In this case, we have unbalanced forces causing the object to move towards the left, the direction that the larger boy is pushing. And in this case, our net force would be 3 newtons towards the left. In the last picture, you have two situations again. Both boys are pulling the chair, and one situation could be that they pull with the exact same magnitude. Both boys pull with 5 newtons of force, making their forces equal, balanced forces. The net force would be 0, and in this case, the object wouldn't move. They're both acting on the chair. They're both pulling on the same object, so the net force would be 0. Another scenario, the smaller boy could pull with 5 newtons, while the larger boy, in this case, could be pulling with 10 newtons. These are unbalanced forces. Net force would be 5 newtons. And in this case, our unbalanced forces would cause the object in question, which would be the chair, would cause the object to move towards the larger boy, since he is pulling with a greater magnitude of force. While playing pickup hockey one day, your friend hits the puck out of your reach. Rather than just waiting for the puck to slow down, you sprint over to it. You know that the puck will not stop easily. But do you know why? An unbalanced force is needed to change the speed of a moving object. So what force is going to stop that puck? Friction is going to be that force that opposes motion between two surfaces that are in contact. Friction can cause a moving object, such as a ball or a puck, to slow down and eventually stop. Friction occurs because the surface of any object is rough. Even surfaces that feel smooth are covered with microscopic hills and valleys. When two surfaces are in contact, the hills and valleys of one surface stick to the hills and valleys of the other surface, and this contact causes friction. The amount of friction between the two surfaces depends on many factors. Two factors include the force of pushing the surfaces together and the roughness of that particular surface. To show you another diagram of how friction works, take a look at this purple box. The pushing force would be the motion of the box, so I'd be pushing the box towards the right-hand side of the screen. But the frictional force is going to oppose that motion, and the frictional force will occur where the two surfaces come together. So that's at the bottom of the box and at the top of the table. The amount of friction is going to depend on that force pushing the surfaces together. If you push down on this purple box harder, the hills and valleys of the surfaces are going to come into closer contact. The closer the contact increases, the friction between the surfaces is going to increase. So if you push it down, you're going to really dig into those ridges and valleys and encounter more friction. Okay, so let's look at this scenario. If I push this wood block across the table, it's going to be encountering a certain amount of ridges and valleys, right? And that would be a fairly large surface area of ridges and valleys. But if you look above those ridges and valleys, you don't have a whole lot of wood above each ridge and valley, but you are going to encounter a lot of ridges and valleys because you have a wider, flatter board. Now let's take that same block of wood and orient it a different way. Let's put it up on its end. Now you're not encountering as many ridges and valleys, but look how much wood you have on top of those ridges and valleys. You're now digging deeper into those ridges and valleys, and you're actually going to encounter the same amount of friction. Even though your orientation is different, you are going to, cancel each other out. The first scenario, you're encountering more ridges and valleys, but less weight of the woods on top each ridge and valley. In the second scenario, you are encountering less ridges and valleys, but you are digging deeper into it. So you're actually going to have the same friction if you kind of calculate it out, which you could using things like spring scales that can measure force pulling an object across a surface, and we'll be doing that in our class. There are two main types of friction: kinetic friction and static friction. We're going to first talk about kinetic friction, and the word kinetic actually means moving. So kinetic friction is the friction between moving surfaces. The amount of kinetic friction between two surfaces depends in part on how the surfaces move. If they slide past each other, if they roll past each other. In this particular circumstance, this particular kinetic friction is called fluid friction because we're interacting with fluids such as water, or you can interact with fluids such as air. Rolling friction is another type of kinetic friction and involves objects rolling across surfaces. And sliding friction, which involves two different surfaces that glide past one another. The other main category of friction is called static friction, and this is when a force is applied to an object, but it does not cause that object to move. Static actually means not moving. The object does not move because the force of static friction balances the force applied. So with these pictures of trophies and vases, gravity's pulling them down, which is a force down, but the table is pushing back up, and those forces are going to be equal, and the friction of the table is actually keeping that trophy in place or that vase in place, and the friction will balance the forces that are applied to the vase. Static friction can be overcome by applying a large enough force to move it, but if you just didn't touch it, static friction would keep it staying where it is. Static friction is essential in life. Otherwise, we wouldn't be able to stand still. Things wouldn't be able to, structures wouldn't be able to keep still. So static friction is very important, and it will disappear as soon as an object starts moving. As soon as it's moving, now it has kinetic friction. Okay, this is just a warning. Friction can be helpful or it can be harmful. So I'm going to really quick go through the pros and cons of how friction can be helpful or harmful. The pros are when you're writing on your paper with like your pencil, friction's helpful. Otherwise, we wouldn't be able to get a grip on our pencil and have our graphite hit the paper. There is friction involved in there, so that's how it's helpful. In ice skating, it's kind of good, or hockey, it's good to have like low friction. We need a little bit of friction with the ice and the blade so we can stop, but there's going to be less friction, and that's how that sport is designed. We also have a lot of friction with our cars, with the treads of our cars, with the engine in our cars. This is important. It helps us brake. It helps us grip the road and not slide around. Friction is important, as well as like on our bikes. We need friction in order to ride our bikes. But for the con side, friction could be bad because we could have parts rubbing on each other in our engine and break our engine. On our bikes, we could have the chain rubbing on other pieces of metal. That could be a con. I have other cons, like my son always rips holes in his pants and his knees because of the friction with the pavement, or he's sliding around on the gym floor. We get friction. We get holes in our socks from friction. That's a bad thing too when you rip through your sock. Air resistance could be a con with our cars. We're making our cars very aerodynamic so they can be fuel efficient. So we do things in order to help with the friction. Like we can add lubricants to help reduce friction. We can add sand to the road to increase friction. So we have scrubber pads to get like dirty dishes clean. So there's all kinds of ways that we can either reduce friction or increase friction depending on the situation that we have.